Welcome to Cambridge IGCSE Physics, Lesson 6.1, Forces and Springs. Today we explore how forces affect springs, examining extension, compression, and elastic behaviour. This core content lesson builds fundamental understanding of force effects on materials. We'll investigate how springs respond to applied forces, analyse their behaviour mathematically, and connect these principles to real-world applications. Understanding spring behaviour is essential for engineering, technology, and scientific research. Let's begin our systematic exploration of forces and springs. Let's examine our learning objectives for today. By the end of this lesson, you will be able to: first, know that forces may change the size and shape of springs. This means understanding how applied forces cause springs to stretch or compress. Second, understand extension and compression of springs. Extension occurs when springs lengthen under tension forces. Compression happens when springs shorten under compression forces. Third, describe elastic behaviour and deformation. Elastic means returning to original shape when forces are removed. These objectives align with Cambridge IGCSE assessment objectives: A01 for scientific knowledge, A02 for problem-solving application, and A03 for experimental skills. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, spring, an elastic object that stores energy when deformed. Springs are made from materials that can return to their original shape. Second, extension, the increase in length that occurs when a spring is stretched by a tensile force. We measure extension in meters. Third, compression, the decrease in length when a spring is compressed by a compressive force. This is the opposite of extension. Fourth, elastic, describes materials that return to their original shape when the applied force is removed. Understanding these terms precisely is crucial for Cambridge IGCSE success. Let's explore our first core concept: spring behaviour under forces. The fundamental principle states that forces change spring dimensions. This means when you apply a force to a spring, it will deform by either extending or compressing. The definition is, when force is applied to a spring, it deforms by extending if pulled or compressing if pushed. Mathematically, we express extension as new length minus original length, where extension is measured in meters using SI units. The diagram illustrates this clearly. On the left, we see the original spring at 10 centimeters length. On the right, the same spring extends to 14 centimeters when force is applied. The extension equals 4 centimeters. Notice how the coils spread apart under tension. This principle is fundamental because it explains how springs store energy. Now we examine the experimental method for investigating spring extension. This follows Cambridge IGCSE standards. The apparatus needed includes a spring for testing, masses to provide known forces, a ruler for measuring length, and a clamp stand for secure mounting. The method consists of these steps. First, clamp the spring vertically and measure its original length. Second, add a known mass and measure the new length. Third, calculate the extension by subtracting original from new length. Fourth, repeat with different masses. Safety is paramount. The hazards include spring failure and falling masses. Therefore, you must secure the clamp stand properly and avoid overloading the spring beyond its elastic limit. Record all measurements in a table with proper units. Let's work through our first example. The problem states, a spring has original length 15.0 centimeters. When a 2.0 Newton force is applied, the new length is 18.5 centimeters. Calculate the extension. We are given original length equals 15.0 centimeters and new length equals 18.5 centimeters. We need to find the extension in centimeters. Step 1. Write the equation. We use the extension formula, which is extension equals new length minus original length. Step 2. Substitute the values. We write extension equals 18.5 centimeters minus 15.0 centimeters. Step 3. Calculate. 18.5 minus 15.0 equals 3.5. Step 4. State the answer. The extension is 3.5 centimeters to two significant figures. Example 2 demonstrates compression, which is the opposite of extension. The problem is, a spring is compressed from 20 centimeters to 16 centimeters. Find the compression. The data shows original length of 20.0 centimeters and compressed length of 16.0 centimeters. Now we analyze. First, identify compression direction. The spring becomes shorter, so this is compression, not extension. Second, apply the compression formula. Compression equals original length minus compressed length. Third, calculate the compression value. 20.0 minus 16.0 equals 4.0 centimeters. Fourth, state the result with units. The compression is 4.0 centimeters. The diagram shows the spring before and after compression, with forces applied from both ends, causing the coils to compress together. Mathematical skills are crucial in physics. Let's examine 3 key skills for spring analysis. First, elastic versus plastic deformation. Elastic deformation means the spring returns to its original shape when the force is removed. The spring behaves like a rubber band. Plastic deformation means permanent change in shape, even after removing the force. The spring has been stretched beyond its elastic limit. Second, measuring techniques. Use a ruler for length measurements, reading to the nearest millimeter for accuracy. Always record the original length before applying any force, as this is your reference point. Third, data analysis. Calculate percentage change using the formula change divided by original, multiplied by 100%. This helps compare different springs. Also identify patterns in force extension relationships, which often show proportional behavior within elastic limits. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a spring extends from 12 centimeters to 17 centimeters. Calculate the extension. This tests your understanding of the extension formula. Question 2 is intermediate. It states a force of 5 newtons compresses a spring by 2 centimeters. Describe the deformation. This requires you to apply compression concepts and explain the physical process. Question 3 is advanced. The question is, explain why springs return to their original length when they behave elastically. This tests your analytical understanding of elastic behavior and molecular structure. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how today's concepts apply in practice. In technology, car suspension systems use springs to absorb road bumps and provide smooth rides. The springs extend and compress as wheels encounter uneven surfaces, demonstrating elastic behavior. In scientific research, force measurement devices called spring balances rely on spring extension to measure weights and forces accurately. The extension is proportional to the applied force. In engineering, building shock absorbers use spring principles to protect structures from earthquake damage. These applications show why understanding spring behavior matters. Career-wise, this knowledge leads to mechanical engineering designing machines, materials science developing new spring materials, and automotive design creating better suspension systems. The aerospace, construction, manufacturing, and research sectors all need professionals who understand force and spring relationships. Let's review the solutions. For question 1, the answer is extension equals 17 centimeters minus 12 centimeters, which equals 5 centimeters. This is correct because we subtract original length from new length to find extension. For question 2, the spring is compressed by 2 centimeters under a 5 Newton force. This means the coils are pushed closer together, reducing the spring's length. The deformation is elastic if the spring returns to original length when force is removed. For question 3, elastic springs return to original length because molecular bonds within the spring material store energy when deformed and restore atoms to their original positions when force is removed. Now, exam success tips. First, always show you're working. Even if the final answer is wrong, you earn method marks for correct approach. Second, include units in every calculation step. This is essential for full marks. Third, check if your answer is reasonable. Negative extensions usually indicate calculation errors. Fourth, understand command words. Calculate means find a numerical answer. Describe means state observable features. Explain means give scientific reasons. Let's summarize today's lesson. The key points to remember are: first, Forces change springs by causing extension when pulled or compression when pushed. Extension increases the spring's length, while compression decreases it. This fundamental principle explains how springs respond to applied forces. Second, elastic behavior means springs return to their original shape when the applied force is removed. This happens because the molecular structure stores energy and restores the original configuration. Third, we measure these changes using the formula. Extension equals new length minus original length. Always use consistent units and show you're working. For further study, review the definitions of spring behavior, focusing on the difference between elastic and plastic deformation. Practice extension and compression calculations using different examples. The next lesson covers Hooke's law, which builds on today's work by introducing the mathematical relationship between force and extension. Ensure you understand today's concepts before moving forward as physics builds systematically.